Now you've done the in-class exercise 1 using this conceptual formula to get the covariance and get the standard deviation for x and y respectively. There is actually an easy way to compute R. Here, let me show you why it is workable. So R is the covariance between x and y divided by standard deviation for x multiplied standard deviation of y. If you remember the formula of the covariance of x and y, it equals to sum of the product divided by n minus 1. Then in the denominator, Sx, or standard deviation for x, equals to sum of the squares of x divided by n minus 1. Then you take the square root. Similarly, Sd, y is sum of squares of y divided by n minus 1, and you take the square root of it. Then if we keep the top the same, the bottom could be sum of the squares for x multiply sum of the squares for y divided by n minus 1 multiply n minus 1. Then this becomes like the top stay the same, the bottom. Square root of sum of squares for x multiply sum squares for y divided by n minus 1. As you can see, n minus 1 is the denominator for the top part. It is also the denominator for the bottom part. Therefore, it could be cancelled out. Finally, this formula is simplified as sum of the product divided by square root of SSX multiply SSY. I think at the very beginning of the semester, I introduced the sum of squares. Then I said that sum of squares is important in later more advanced knowledge. It actually being very commonly used in more advanced stats. Here to compute R, we use sum of the squares for x, then sum of the squares for y. Then the denominator is sum of the product. So this formula is actually more easy for us to compute the R. Let's look at in-class exercise 1. X is 11, 13, 18, 12, 16, and there are y's. Then first we need to compute the denominator, sum of squares for x and sum of squares for y. Then we compute the sum of the products. Sum of the products equals to x minus x bar multiply y minus y bar and add them together. Finally, we can compute R. Therefore, it's more straightforward. Okay, following this table, we can compute mean of x and mean of y. Then we compute deviation scores for each x, then deviation scores for each y. Then we compute the products. Then we compute the sum of the products is 27. Then we compute sum squares for x. Finally, sum of squares for y. So R equals to 27 divided by square root of 34 multiply 30, which is 85. This method is much easier than the conceptual one you did before. Now you can take out in-class exercise 2 and compute the correlation coefficient using this new formula. Finally, I want to remind you that if two things or two variables are highly correlated, it does not mean that x causes y. Therefore, a relationship or a correlation does not equal to causation. Here is an example. Given a correlation of ice cream consumption and a case of drawing, you may speculate ice cream caused drawing. In fact, study or data showed that ice cream consumption is highly correlated with number of drawing. R is as high as 0.70. Can we conclude that eating ice cream causes people to draw? And why not? Therefore, can conclude that high correlation does not imply high causation. It's very important that you understand what your data means, and you understand what a high, either positive or negative correlation could be explained. It only means that two variables are covariant with each other. In other words, one variable changes, the other variable changes along. But there are many reasons why two things could co-change together. Okay, today we learned correlations. First, we introduced the scatter plot. Then we talk about the three properties of a correlation: the direction, the form, and the strength. We explained covariance between X and Y, and why we cannot use covariance to indicate a correlation or to indicate a relationship. Next, we computed and interpreted the Pearson correlation coefficient. We used both the conceptual method and a computational method to get an R. Finally, we differentiated between correlation and causation.